Good evening, ladies and gentlemen. How is everyone doing? I'm also well, thank you. So tonight is a question and answer session, or you can call this a recap session of the work we've done. So I'm not going to go through any specific work. The idea of this class is that you guys can ask me questions and I can help you understand the work better or explain things in a different way to help you prepare for the test. And you can also discuss the work amongst yourself as well during this session. So I'm going to open up the floor to you guys and ask if you have any questions, something you don't understand, something you need to know about this test. So which section would you prefer we start with? So everything, chapter 1 to 10, just go through it sequentially. So are we going to go over the mock test as we are going to check and see if our answers are correct? So yes, we are going to go through the mock test in tomorrow night's lecture. The reason I'm doing that is I've received a flood of emails asking if we can do it tomorrow night. It seems like there's a lot of students writing tests tonight and also tomorrow sometime. So I asked if we could do it tomorrow night. So tonight we are just going to have question and answers, if you're going to have questions and answers. So question, so is the mock test a good measure of how the test will be? Yes, it is. Will the entire test be a multiple choice format like the mock test? So 90% of the test will be multiple choice. The rest will be a little bit longer questions. So to give you more details on the test will be 2.5 hours. I will open it up at 5:30 and close at 8 o'clock. See, the marks allocation is 58 marks. So from that 58 marks, there are 50 questions. From that 50 questions, 46 questions is multiple choice. And then the remaining questions are a bit longer questions. A good example of something that I can ask for the longer questions is to do something like describe the 4 most significant discoveries of Galileo. Then you have to know it is the moon has craters, Jupiter has moons orbiting around it, Venus has different phases, and he's also seen that the moon has sunspots. So those are the type of long questions I can ask. It is a pleasure. And then one thing I want to ask you guys is please determine beforehand if you are going to have load shedding during that time. If you have load shedding, then you please send me an email so I can open up the test for you a bit earlier or a bit later, depending on your load shedding. And then one thing I also like to do during these online tests is I know there's a bandwidth problem and data problem. If you're struggling with bandwidth and data, but I'm going to have a Blackboard Collaborate session open during that time. So during that time, if you have any questions, then you can just unmute your mic or type in the chat and I can immediately assist you. Or you can just raise your hand in the chat in Blackboard Collaborate, and I can also assist you during that time. And I will also give announcements such as time warnings as well. Any questions? Does the emission spectrum refer to low density gas only? So it all depends on your type of emission spectrum. So remember the Kirchhoff's laws. So let me just see if I can quickly, can you guys remember which slide that was? So you guys perhaps, I can't remember hard which chapter was the spectrum. So I think it was one of the earlier chapters. Now let me quickly see what I can find. So I'm struggling with finding distance between other planets relative to Earth and the Sun, such as in the mock test or in the quiz. Is that what you're asking? And then, sir, how much do students on average get for the semester test as in from previous years? So last year's average was 68%, and the year before the average was 65%. So it's actually quite high averages. Lecture 7. Okay, so let me open up lecture 7. Can you remember what slide in lecture 7? No, you don't need to know dates. Let me see if I can get Kirchhoff's laws. That's what helps a bit if you can tell me beforehand which lecture slides it is. Let's see where I can get Kirchhoff's laws. I think it's in chapter 6, lecture 6, I think. Let me quickly see. Look at atoms and spectra. Let me see what I can upload quickly. So you are asking about an emission spectra, right? So the three laws of Kirchhoff is we get an continuous spectrum from a luminous solid or liquid or dense gas. So if we are looking at a light source, for example, or a star or a gas object or liquid object, we will receive a continuous spectrum from that object. And then we get an absorption spectrum. That is if we have a light source on one end and we have a gas cloud in front of the light source or the source of radiation. So the continuous spectrum going through the gas cloud now absorbs a certain part, and that's absorption spectrum. And then emission spectrum is when we have a low density cool gas in front of a hot source that emanates a continuous spectrum. It's a dark line absorption line, and then a low density gas seen against the cooler backgrounds emits a bright or emission line spectrum. So when we don't have a object in the background emitting radiation, and so it's basically a cold background, and we have a low density gas, and we look at low density gas, and that will emit a spectrum. Does that help? So yes, the mock test is a good measure of the knowledge of the work. So that's remember, if you have a cold background with a low density gas, then that is an emission spectrum. If you have a warm background with a low density gas, that's an absorption spectrum. And if you just have a, let's call it again, a warm background, so that means the object radiating, that will radiate against all frequencies, that is a continuous spectrum. Let's see if I can quickly show you a nice image that will explain this better. Can everyone see the image? So with a continuous spectrum, we will have our source that's radiating electromagnetic radiation at all frequencies, and we will see it as a continuous spectrum. Again, if we have our object that's radiating electromagnetic frequencies or EM frequencies, and we have a low dense gas cloud, then that low dense gas cloud will absorb certain frequencies, and that's the absorption spectrum. And then when we have where the background doesn't have a EM source, but there's a gas cloud, then that will emit a certain frequency, and that's called an emission spectrum. And these are the three classes of spectrum you get, and these are also known as Kirchhoff's three laws. So this continuous spectrum is law 1, absorption spectrum law 2, emission spectrum law 3. Do you guys have any other questions? Not right now. Which is the contradictory evidence for the Milankovitch cycles? Okay, so let me go to the contradictory evidence. Yes, tomorrow is also a question and answer session. So tomorrow we will go through it and so let me quickly get this for you. So basically the Milankovitch cycles describe that Earth goes through cycles, that it cools down a bit and warms up a bit. It cools down a bit and warms up a bit. And if you do a bit statistic on it, it is almost 100-year cycle. So what was proposed that the global warming was just part of the Milankovitch cycle, that we're now part of the cycle where Earth heats up again. But if you plot the CO2 emissions from the Industrial Revolution and what we're doing now against it, we can see, yes, the Milankovitch cycles is happening. We are getting hotter and we are getting colder, but due to CO2, the contradictory evidence is that due to CO2, the cycle has become more extreme, first of all. So when it gets more hotter, it gets extremely hotter. When it gets cooler, it gets extremely cooler. And then secondly, what the cycles doesn't account for is the average temperature of each 100-year cycle that continues to climb, and that is the contradictory evidence. When asked how many dimensions are there, going to be 40, 60, or 11? So for all intents and purposes, we are working in 4 dimensions. So during the lectures, there are moments where we meet some sections which are reasoning with numbers. I just want to ask if we have to answer questions whereby we will need those formulas. Yes, so those formulas, I will give you that formulas in a formula sheet. But yes, those are the typical calculations that you will need to do, especially regarding calculations for the apparent visual magnitude. So I can give you, for example, the brightness of 2 stars, and you have to determine by making use of the equation which star is the brightest and how much brightest. Is it 4 times brighter, 16 times brighter? So it's straightforward questions. So if you have the formulas, just plug and play, but you need to know how to use those formulas. But it's basically easy, straightforward plug and play. Could you please demonstrate what an ecliptic is on a whiteboard, or perhaps using a picture? Okay, so let me get you a picture. So after the plug and play, do we have to interpret the answers, a full sentence, but no, you will just pick the answer from the multiple choice questions. So it's really straightforward. I don't want to catch you out or make your life difficult. Let me see if I can get you a good explanation for the, yeah, this will work. Let me just quickly upload this image. That's not that one, we want that one. Why doesn't this image want to load? This is weird. Let me upload that again. Okay, share. Why can't I upload this file? Let me try this again. So it seems like Blackboard is picky about formats we can upload. So let me try this again and upload as a PNG. Okay, can everyone see the image? Okay, cool. So let me get a color out that you guys can see easily. So I assume red will probably be, not red, stack it, that's on screen. So here we can see is Earth in the center. So this is the cant that Earths make. So that is roughly the 21-degree angle. So basically 21-degree angle. And the ecliptic is basically the direction or the path around the sun. So if we look directly to one side, we see the Earth directly head on from the equator. And this disk it forms is the ecliptic. But the ecliptic also, you can see the ecliptic also in the night sky. So let me show you a picture of the ecliptic in the night sky. If I can find a good picture for it. Is it not 23.4? Yes, it's 23.4, but I usually, for some reason, have 21 degrees stuck in my head. But yes, if you round it, it's usually 23 degrees. So this image will work. this image. Oh, this is a very bad resolution image. Let me see if I can get one that is better. No, you won't need an HR diagram, but I will in any case give you an HR diagram. But there is no need to have one by hand. I will supply you with one. You just need to know how an HR diagram works. But for the questions I'm asking for the test, you don't need an HR diagram. So this is a bit better image. So this is the ecliptic. So you'll see this ecliptic. And what's also important, all the other planets also orbit around the sun in the ecliptic. And that is how star signs work. If we are behind Earth and we're looking towards the sun, the direction it points in is the star sign currently, and that is how horoscopes work. And astrology work, that is totally rubbish. But that's basically the principle behind it, and that's the ecliptic. And can you guys guess why we can see the Milky Way overhead at night and it's in dark places? So the center of the Milky Way is at an angle to the ecliptic. So it's not in the same plane as the ecliptic, but it's slightly off center, and that's why we can see the ecliptic overhead at night. Not the ecliptic, the center of the Milky Way. Pleasure. Do you guys have any other questions? So yes, the test on Friday is a closed book test. So what is the term semi-axial on Kepler's third law, lecture 2? Let me open up lecture 2. Can you remember which slide in lecture 2? Number 34. Lecture 4. Okay, let me have a look. Lecture 4. Lecture 4, slide 34. You sure it's lecture 4? So lecture 4 is slide 34 is observations on Earth optical and radio telescopes. Okay, Kepler's third law, lecture 2. So, okay, got it at lecture 3. Okay, so let me upload this slide again. So the slide is being uploaded, and no worries. I know it's a lot of slides and a lot of work. So it's now being uploaded. Its slide is still uploading, but basically the second law of Kepler states, let me just open it up, third law. The second law states the imaginary line joining a planet and the sun sweep equal areas of space during equal time intervals as a planet orbits. I apologize for cut out, sir. Load shedding expected where I live. No worries. This is being recorded and I will upload it as soon as we end this at 6:30. I apologize for this for taking so long to upload. For some reason, if you upload a file to Blackboard Collaborate, then Blackboard Collaborate converts it to its own format and compresses it a little bit. But while it's uploading, I can draw it perhaps. So what a second law of Kepler actually means is, if we have the sun over here, and Earth is orbiting, or any other planet is orbiting around the sun in an ellipse. So let's draw Earth perhaps over here. So that means is, if we divide this in areas, so this area right here will be more or less the same area as over here. So we can call this area A1 and this area A2. So to cover this area over here, we'll take 1 month, and this area over here will also take 1 month. So what it means is, let me get a point out. So during these two segments, the Earth is not traveling at a constant speed. So at certain parts of it orbits a little bit faster, and in certain parts of the orbit, it orbits a little bit slower. So what it means is a radius vector joining any planet to the sun sweeps out equal areas in equal lengths of time. So from this, it is important to know that area 1 equals area 2. And that is basically Kepler's second law. Does that answer your question? And what is the semi-axis? Which slide exactly do I state semi-axis? Slide 34. Okay, that's Kepler's third law. So let me just quickly find a slide. Okay, I see what you are asking. Let me just see if I can get a way to. Okay, so basically what it comes down to is, so this is our, so let me just clear this board. It'll be easier to explain. But what this actually means is it's just a geometry construct. So this is our ellipse. Here is the center of our ellipse. So remember, the sun is usually at one end of the ellipse. So what this means is, basically the semi-major axis, if you take the center of the ellipse to the furthest point of the ellipse, center to furthest point, that is the semi-major axis. So let me see if I can get you a good image to explain this. I think this should do. So in this image, we can see our ellipse. Here is the center point of our ellipse. Here is the sun. So from the midpoint ellipse to the furthest point away, so we're over here, or it could be over there, that is the semi-major axis. Does that explain it a little bit better? And then from this, it's also to note, if we are orbiting around a body, so the Earth and the Sun, so where these two orbits are closest to one another, that is called perihelion, and where they are the furthest away from each other, that is called aphelion. And then also one other thing to also take note, that's in the slides, but just to recap, let's draw a little radio telescope. So if this is our telescope, the point directly above the telescope, so 90 degrees above your head, that is called azimuth. Sorry, not azimuth, that's zenith. So that is our zenith point. So if we are observing, say, for example, a star over here, then the angle this makes over from here to here, this is the altitude above the horizon. And then if the telescope, we don't speak about moving left or right, we move the telescope, can turn in a circle around, and that circle around is called the azimuth movement. But this point here is called zenith. And then the opposite is if we go in the opposite direction, so 90 degrees below the telescope, that point is called the nadir. Okay, any other questions? Anybody else? Anything else I can help you guys with? So what did Galileo's discoveries prove again? So the four most important things of Galileo's discoveries was, one, the moon has craters. Secondly, Jupiter has moons. Thirdly, Venus has phases. And then lastly, the sun has sunspots. Pleasure. So tomorrow night's lecture, we're going to do the exact same thing. You guys can answer questions, I will explain it, and we will go through the memo of the mock test as well. So I'm going to remain active for another minute or two if you have questions. If you have no further questions, you guys are more than welcome to log off. And I will see you all in tomorrow night's recap lecture. I've sent on a group for you guys that's interested and have time. Dr. Sheldon Harps from UJ is giving a talk on relativity tonight. The talk is for the West Rand Astronomy Club. It's virtual. It's on Google Meet. So I've sent the link, so you guys are more than welcome to listen to that as well. Otherwise, have a wonderful evening, and I will see you guys all tomorrow night for the last recap lecture. Yes, before I forget, I want to ask you guys this. Do you need me on campus tomorrow? Because there's some other stuff I can work on at the observatory. that needs my attention. So if we can do virtual consultations, that would be great. But if you really want to see me face to face, then I can be on campus. I will ask that on the group as well, so democracy will decide. Okay, then I will post it now on the group as well. Okay, otherwise have a great evening, everyone, and I will see you tomorrow. Question. For those of us writing tomorrow, can we send questions on a group instead and watch the recording for the answers? Yes, you can do that as well. It's a pleasure. You can send it on a group or you can email me. I just wanted to ask a couple of questions about a prep work I've planned, nothing too much. That's what I wanted to know. So will a virtual consultation work for you? Can you just send me an email, then I will reply to your email with a meeting invite. And just in your email, just state what time tomorrow will work for you, and I will send you a virtual meeting invite. Awesome. Thank you. Have a great night, everyone.